You type google.com. You press enter. The page loads almost instantly. Feels simple. It's not. In under a second, your device just performed DNS lookups, network routing, encryption negotiation, server computation, and real-time rendering. Let's walk through it properly, from the moment you hit enter to the moment pixels appear on your screen. Step 1. The browser reads what you typed. Let's say you type https://www.example.com/products/phone. Your browser immediately breaks that into pieces. HTTPS. That tells the browser to use encrypted communication. www.example.com. That's the domain. Humans understand this, computers don't. /products/phone. That's the specific resource you're asking for. The browser now knows what protocol to use, which server to contact, and what resource to request. But it still has a problem. Computers don't speak domain names. They speak IP addresses. Step 2. DNS, turning names into numbers. DNS stands for Domain Name System. It's basically the internet's phone book. Before your browser asks the world, it checks locally. First, the browser cache. If you recently visited the site, the IP might already be saved. Then, the operating system cache. Your OS keeps its own DNS records. Then, your router. Your home router may have cached it. Then, your ISP. Your internet provider often caches popular domains for millions of users. If none of those have it, a full DNS lookup begins. The real DNS lookup. Your device asks a recursive resolver. This might be your ISP's DNS server or a public one like Google 8.8.8.8 or Cloudflare's 1.1.1.1. That resolver does the hard work. 1. It asks a root name server. There are 13 logical root server systems worldwide. They don't know the final IP, they just say ask the .com servers. 2. It asks the .com TLD server. That server says ask the authoritative server, for example. 3. It asks the authoritative name server. This one finally responds with the IP address. The resolver sends that IP back to you and caches it for next time. This entire process usually takes between 20 and 120 milliseconds. But here's something most people miss. Each DNS record has a TTL, time to live. Once it expires, the lookup has to happen again. Step 3. Local network check, ARP. Before your computer even talks to the internet, it needs to know something else. What's the MAC address of the router? Inside your local network, devices use ARP, Address Resolution Protocol, to map IP addresses to physical hardware addresses. If your computer doesn't know your router's MAC address, it broadcasts a request across your local network. That happens in microseconds, but it's still part of the chain, establishing a TCP connection. Now your browser has the IP server. To send data reliably, it uses TCP. This starts with the famous three-way handshake. SYN, I want to connect. SYN-ACK, okay, let's connect. ACK, connection confirmed. Now both sides agree on sequence numbers so data arrives in order. Why TCP? Because the internet drops packets sometimes. TCP guarantees reliability and retransmits lost data. Without it, websites would load broken. TLS handshake, locking the connection. Since you typed HTTPS, encryption kicks in. Modern browsers use TLS 1.3. Here's the simplified version. Your browser says, here are the encryption methods I support. The server responds, here's my certificate. Here's the encryption method we'll use. Your browser checks the certificate against trusted certificate authorities. If it fails, you see your connection is not private. If it passes, both sides generate shared encryption keys. From this point forward, everything is encrypted. This usually adds 50 to 100 milliseconds. And yes, without this step, anyone on your Wi-Fi could read your passwords. The HTTP request. Now your browser can finally ask for the page. It sends something like get/products/phone. This includes headers, host, user agent, accepted content types, cookies, language preferences. Cookies are important. They might contain your login session ID. That's how websites remember who you are. Modern websites often use HTTP2 or HTTP3. HTTP2 allows multiple requests on one connection. HTTP3 is even faster. It runs over QUIC, which uses UDP instead of TCP, reducing handshake time. What happens on the server? Now the server receives your request. If it's static content, it just grabs a file and sends it. If it's dynamic, it runs backend code, queries a database, checks authentication, applies rate limiting, logs analytics, generates HTML. On big websites, this may happen across multiple servers and microservices, often behind load balancers distributing traffic. And if the site uses a CDN, something else happens. CDNs, why distance matters. Large websites use content delivery networks like Akamai Technologies or Amazon Web Services. Instead of your request traveling across continents, it's routed to the nearest edge server. CDNs use anycast routing to automatically direct you to the closest data center. That cuts latency dramatically. Step 8. The HTTP response. The server sends back status code, headers, the HTML body. 200 means success, 404 means not found, 301 means redirect, 500 means server error. Headers may also include caching rules. For example, cache this for 1 hour. Your browser respects that. Step 9. Rendering the page. Now your browser has HTML, but you still don't see anything yet. Here's what happens. 1. HTML becomes the DOM. 2. CSSO becomes the CSOM. 3. They combine into a render tree. 4. Layout calculates positions. 5. Paint draws pixels. 6. JavaScript runs. JavaScript can modify the DOM, request more data, and change what you see. This is why pages sometimes shift after loading. It's also why slow JavaScript can block rendering. Modern browsers use rendering pipelines optimized for speed, often spreading work across CPU cores and GPU acceleration. Hidden speed tricks. There's even more happening. DNS prefetching, pre-connect, resource prioritization, compression like Brotli, persistent connections, browser caching rules, service workers for offline support. That instant feeling is actually aggressive optimization layered on optimization. The big picture. When you press enter, your device translates a name into an IP, finds the router, builds a reliable connection, encrypts it, sends a structured request, triggers backend systems, receives structured data, builds a visual tree, paints pixels, all in under a second. That's not simple. That's coordination across global infrastructure. Next time you press enter in your browser, you'll know the invisible miracle happening behind the scenes. Which step surprised you the most? Drop it in the comments. And if this deep dive into internet infrastructure blew your mind, hit that like button and subscribe for more tech explained at the deepest level.